Alright, y'all, this is the homework 3, homework in heat, just in case you weren't here. I'm going to go over a couple of these real quick, and then just kind of cut you loose and everything. So this one, compare the work done by friction along the two paths. This isn't as hard as you think it is. Like, look, from A to B, this is a square, okay? It's a square, so each leg is equidistant. So look here, A to B is one leg versus A, PB. That's 3 legs, so that should kind of tell you, like, look, this guy's walking 3 times as far, you're dragging it 3 times as far. So that's it for that. Alright, now this one right here, very similar to problems we had in the previous chapter. So real quickly, so that right there is mass, that's velocity. This is question 9, by the way. You really don't need this because look here, what is the mechanical energy loss? So the ME is what? We're not going from a situation where you started up high and then dropped low, so we don't have like kinetic and potential, we don't have a roller coaster or anything like that. So you're strictly just working off of the energy based on your motion, which is kinetic energy. So in this case, since you're not changing potential energy at all, your mechanical energy, this is a given you have to put, is kinetic energy. All right, so what is our kinetic energy? It's our mechanical energy because we don't have any change in potential energy. All right, so our ME is our kinetic energy because that's the only energy that was involved in this problem. What is our equation? If we look at our equation sheet, which you should have to do these problems, it's 1/2 mv squared. You might even write in your equation sheet somewhere that ME can be equal just to this. If you look at your conservation of energy or mechanical energy equation, it's PE plus KE. And just make a note to yourself that sometimes this might be gone, or the KE might be gone. Just make a note to yourself somewhere. Anyways, so we're going to plug in our M, which is 76.9, our V, which is 4.66 squared, and then you just put that over 2, that's 1/2, and that'll get you your answer. Okay, so this is the next problem, number 10. This is the exact same thing. So you are, even without looking at the problem, we can still do it. Determine the work. So our work is what we're given is our mass, and our radius here, which ends up being also 49 here, is our height. So we have MH. We also know that gravity, or gravitational acceleration, is always 9.8 in this case. So look here. Remember the work energy theorem, that work is equal to the change in kinetic energy, but it's also just equal to change in energy in general. All right, if I push something up in the air from here to here, I did work on it. It's force times distance. The weight times the distance that I raised it against gravity, that'll change the potential energy, right? So in this case, all we're doing is our work is equal to energy. What energy in particular are we talking about? We're talking about potential energy, and you know the equation for that. So after that, you're really just doing MGH there. All right, now this is kind of an interesting one here. This is working off the exact same problem. If the kinetic energy at the bottom is 5,900 joules, this is our kinetic energy final. What is the work done against friction? So we call this non-conservative. This is non-conservative. Okay, so in the previous problem, we said that the work was equal to potential energy. Our work was equal to like our mechanical energy that was done on the block sliding down the ramp. It turned out to be this. I didn't calculate it out or anything, but I mean, you could have done that just by extending the problem. In fact, I encourage you to pause these videos and try to work these out and make sure you get the answer that I have in the bottom of each one. Now, this one is telling you that I should have converted this much energy because gravity was working on the block and making it come down the ramp, right? Making it come down the ramp like this. I'm going to get rid of this real quick. By this coming down the ramp, gravity was doing all the work and turning it into kinetic energy. What I'm saying in this problem, though, is that when I did all that work, I only ended up with this amount of energy, but I should have had that, right? So the work done against friction, against what was the work done by non-conservative forces, it's going to be the difference between what I should have had and what I actually had at the bottom. So I should have had this much kinetic energy. This is my kinetic energy ideal. This was my actual, okay? So what ended up happening there, remember my mechanical energy is equal to potential plus kinetic plus the work, right? I don't have potential because I'm at the bottom, there's no height. So how do I solve for work? I subtract kinetic energy. Cool. And so when you subtract those numbers, you end up getting this guy right here. Okay, this one we've done in class already as a warm-up, but I want to show you this again. Initial internal energy, so this is delta U initial. I'm use different colors, that kind of sucks. All right. So my delta U initial is 30. Then heat is added to the system, so our Q is going to be a plus. It's going into the system. Remember, you have to use these key terms to kind of understand if this is my engine going in, this is out, in, and this would be my internal energy, which is kind of like these things happening right here, right? So you can kind of see it like that. This was a picture you drew in your notes for vocabulary. The final internal energy, so this is my delta U final, delta U F, and the system does, which means it goes out, which means it's negative, right? 21 joules of work, right? How much heat is added to the system, so I'm looking for my Q, right? Okay, so remember, this is the first law of thermodynamics, which you do not have in your formula chart, so you need to make sure you have this. All of y'all should. It's changing U equals W plus Q, and you can do that in any order you want. It really doesn't matter. You're just adding. So let's go ahead and plug in our stuff. So I'm going to go ahead and plug it in right over here. Okay, so my delta U, remember this expands into final minus initial. So delta U final minus delta U initial. Or I'm sorry, it's not delta U, it's just U final and U initial. U final minus U initial equals work plus Q. Okay, my final was 38. My initial was 30. My work was negative 21 because it's going out, and my boom, boom, boom. So I just moved stuff around by adding 21, boom. And we've done this already. You end up with this guy right here. All right, these ones here are kind of confusing, but it's not that bad. So what you're doing here is you're looking at like an energy, you're looking at mechanical energy initial having to equal mechanical energy final. This is conservation of energy. So looky here, that like it's very important that you keep track of the titles and the subscripts. Potential energy final plus kinetic final. I'm just gonna use K because I've got stuff to do. All right, so look here. This plus this has to equal that plus that if you're talking about conservative forces only. Okay, so it's saying the kinetic energy of the particle at time initial, so that's kinetic energy initial, is going to be 14.1. And this is going to be potential 7.1. So this right here, this total has to equal the total on the other side, so that's pretty easy, right? They're giving you what this has to be, right? So when you add this up and subtract the kinetic final, guess what? You should end up with the remainder of the potential final, right? So you're basically just adding these together to figure out what your total should be in the system, and then you're getting the kinetic final and figuring out what part of that should be potential. It's really not that bad, okay? The next part is where it gets kind of hairy, because now it's telling you that there's non-conservative forces in the next problem. So you're still using the same total from up here, right? Still using the same total from up there, which when you added 14.1 and 7.1, you should have gotten 21.2 as your mechanical energy in the system initial. Now, though, when I subtract this guy and this guy, because that kinetic final is still going to be the same. So we're going to go 21.2 is our mechanical energy initial, and this should be equal to my potential final plus my kinetic final plus the work done on the system, right? Or minus the work done on the system because it's leaving. Okay. So let's see. So we're going to subtract the potential minus the potential energy minus the kinetic, and what you'd have over here is the negative work that was done because the work left the system, right? So look here, you notice it's negative, negative. They're going to flip, right? Okay, and that's why you end up with a positive 9.7, right? Because whatever is remaining from subtracting all these numbers would be the work that would have had to have been done. Okay, I'll do this pendulum problem. It really shouldn't be that hard for you, but I'll do the pendulum problem anyways. The height you're dropping is from here to here, and that's what makes this kind of hard. It's really difficult. So you're really this is your height right here. Okay, what you're gonna do for that is this is 2, but you're looking for this right here and subtracting it from 2. And how do you do that? Well, this is I'm not going to go too into it because it's beyond the scope of regular physics, but I'll go ahead and just tell you that this right here ends up being a right triangle. If you're looking from this viewpoint, theta, right there, which just means angle. From that position, what are my missing sides? I have a hypotenuse right here because it's the side opposite of the 90. And from this angle, I would also have the adjacent. Right, I'd have the adjacent. So what sine, if I do so, ka, toa, This is sine, cosine, and tangent. The one I would use would be opposite and adjacent, and this is opposite over, adjacent over. Okay, so that's what's happening right now. I would say it tells you it's a 30-degree angle. Okay, so the cosine of 30 degrees would be, and you don't need to put that in that degree you don't need to put in the calculator, by the way. It would be adjacent over hypotenuse. My adjacent is my unknown. My hypotenuse is 2. How do I solve for the adjacent? Multiply 2 cosine 30 equals my adjacent. Then you just plug that in the calculator, you get it. And whatever this would be would not be your height. This is not your height. This is the entire side here. You're really looking for that. So you're subtracting your adjacent from 2. So you do 2 minus whatever your adjacent was, and that'll be your height. And then you can do potential energy from there. Okay, that plugs into potential energy equation. Cool. Okay, so from here, I'm not really going to get too into it, but I'll just show you the equation at least, because the pendulum and this problem are both going to be bonus for this anyways. So just kind of look and see if you can plug the equation and get this answer correct. But this is my heat energy equals mass times specific heat capacity times the change in temperature. So that's my mass. Be careful because that's in grams and this specific heat is in kilograms, so you'd have to convert this into kilograms by doing the grams is how many kilograms, and you'd go like that. Grams are here. 1 kilogram is 10 to the third, so you're dividing by 1,000, which means you're moving the decimal over 1, 2, 3 times to the left. Okay, half the kinetic energy of the bullet, so you'd have to first get this kinetic energy over 2, and that goes into the heat of the equation, and you just do that. And what are we solving for here? What is the increase in temperature? So you're looking for the delta T equals question mark. So you're solving for this guy right here by, how do you get rid of M and C? Well, they're all multiplying, so you would just divide by MC. Okay, cool. It's kind of a tricky problem, but it's not that bad. All right, hope that helped. Bye.